In this video, we're going to introduce directional derivatives and the gradient vector. So we've already talked about the partial derivatives of a function with respect to x and with respect to y. So that's giving us a rate of how the function changes, or a rate of change in the x direction or in the y direction. So those are two very specific directional derivatives. We're talking about how the function changes if we move in the I direction along the positive x direction, or in the j direction along the positive y direction. So we're going to change this up a little bit. Instead of just having to move along the x-axis or move along the y-axis for our inputs, we'll talk about move along any direction in the xy plane and see how the function changes. So to give you a picture of what might be going on here, the light blue graph is some surface. And I want to know how the surface changes, how the outputs of this function that's represented by this surface changes as I move in this vector here that's starting at the point B and kind of coming out of the screen. All right, so I imagine now taking a plane and making that plane perpendicular to the xy plane through that vector that starts at B. When I do that, I get the intersection with a surface that creates a curve. And now I can think about this particular curve finding a tangent line to that curve, which is what this line is representing. So this black line here is in this plane, and it's tangent to the surface at the point A. The point A lies directly above the point B, so we're thinking about taking the xy coordinates associated with B, plugging into the function, and getting that point on the surface. We can calculate the slope here of this line, and that's what we're going to mean by our directional derivative. So this slope, what that value of that slope is the rate of change of the function in this direction. All right. So let's make this a little bit more firmed up, if you will. We're going to take a point in the xy plane that's h units from the point x naught, y naught. All right, so here's my x naught, y naught in the xy plane. Here's my xy, and I want this distance to be h. The vector u here, we're going to assume is a unit vector, so that when you calculate HA and HB in this direction, here's my HA, here's my HB, that's actually corresponding to getting this unit h here, right? Because if I do Pythagorean theorem, I would have h squared a squared plus h squared b squared. Well, if I factor out the h squared, I get a squared plus b squared. If u is a unit vector, then I just get h squared, which is the right distance for our hypotenuse here. All right, so this is our setup. My point, this would be right here at the end of this dashed line in the xy plane. That would be the point xy. And right here, this would be the point x naught, y naught. So the points that are up here are on the surface. We would get those by plugging in the x naught, y naught into the function. I would plug the xy into the function. All right, if my point xy is in this unit direction and it's h units away, I already established that we can go out HA and over HB, if you will. So I can calculate the x and the y by starting at x naught and going AH in the x direction, start at y naught and go BH in the y direction. So I can write my x and y in terms of those values. Now we can calculate slope in the usual way. Our slope, if you think about it, is rise over run. Well, our quote-unquote rise in this case is the difference in the outputs of the function. So it'd be f of xy minus f of x naught, y naught. Our xy here, these are our values for our xy in terms of x naught, a, and h. Our run is that distance that we're going. We're going h units in the u direction, so I would just divide by the run in this case, which is just h. So this is how we would approximate the slope. And then just much like what we did in Calculus 1, we'll let the h go to 0, and this gives us our definition of our directional derivative of the function f of xy in the direction of a unit vector. And again, we need a unit vector for this computation to work out here. All right. So that's our definition of our directional derivative. So we let u to be a unit vector, write it as a comma b, but in this case we force the magnitude to be 1. The directional derivative will be this limit, like we said on the previous slide, provided, of course, that the limit exists. That's exactly like what we would say in a Calc 1 sense. All right. Certainly, if all we have is a table of values or contour maps for a function, then we would need to use this definition to help us estimate a derivative. However, if we're given an explicit function, it's much easier, typically, to calculate the directional derivatives with the following theorem. And that theorem is that if I can find the directional derivative in the direction of a unit vector u by taking the dot product of the vector formed by the partial derivatives with respect to x and y with that unit vector u. So we get the partial derivative of with respect to x times a plus the partial derivative with respect to y times b. That gives us our directional derivative in the direction of u for our function. Do a quick little proof here. Let's set our g of h to be f of x plus ah, y plus bh. So what looks like here, that kind of the first term in the numerator in our directional derivative definition. If I want to take the derivative at 0, well, this is a Calc 1 concept because I'm looking at a function of one variable. I can calculate the derivative at 0 as the limit as h goes to 0 of g of h minus g of 0 all over h. Plugging in our pieces that we know for each of those things. If I put in 0 for h, this is exactly what we get here. I get f of xy. I put in h for h. I just get this expression, but we recognize this by definition as being the directional derivative. Calculating g prime of h in a different way, we can use the chain rule. The chain rule says that if I want the derivative of g with respect to h, I can take the derivative of f with respect to x and then multiply by the derivative of x with respect to h and do the same thing for y and add them together. That's our chain rule for a function of two variables. Well, this is the partial with respect to x of x plus ah, y plus bh times a, because that is the derivative of x with respect to h. Similarly for y, get the same type of expression just with a b on the end. And then if I put in 0 for h, I get the partial with respect to x of xy times a plus the partial with respect to y times b. And the result follows because that has to equal the expression that was on the previous slide, namely the directional derivative. Let's see how I can use this. Let's say we're asked to find the directional derivative of the function x e to the 2y at the point 2, 0, and in the direction of the vector v, which is 3, negative 4. First, we calculate our partial derivatives. Partial with respect to x is e to the 2y. Partial with respect to y is 2x e to the 2y. Remember, for directional derivatives, we need a unit vector in the direction that we're interested in. So I need to get a unit vector in the same direction as v. So I take v and divide out by the magnitude of v. So I get 1/5 of the vector 3, negative 4. So now if we do our directional derivative, we do the dot product of our unit vector and that vector formed by the partial derivatives. So in this case, if we plug in the point 2, 0 into the function, or into our partials, pardon me, I get 1 for the x component and 4 for the y component. And we do the dot product there, we get negative 13/5. All right, so this vector that we had in the first part of the directional derivative leads us to a definition that we call the gradient of the function. So the gradient is the partial with respect to x times I plus the partial with respect to y times j. It's those components. It's that vector that we talked about that we were dot producting with the unit vector in our directional derivatives. So this is our definition of the gradient vector. This is our notation for the gradient vector, that upside down delta. We can also do gradients for functions of 3 variables. And it's defined similarly. We just have a 3-dimensional vector rather than a 2-dimensional vector. So looking back now at our directional derivative, we can calculate the directional derivative as the gradient times the unit vector. So let's look at an example putting this gradient definition to use. So let's say we have the function f of x, y, z equals e to the y, z cosine x. Let's find the gradient of f and then use it to find the directional derivative at the given point in the given direction. All right, so again, to find our gradient, we'll do the partials with respect to each of the variables times their respective I, j, k, the unit directions in those respective directions. Derivative of cosine x is negative sine x, so the derivative with respect to x is e to the negative yz sine x. Derivative of e to the yz with respect to y is z e to the yz, and then times the cosine x, that'll be times j, and then we'll have a y e to the yz times cosine x times the k. For a directional derivative, so that's our gradient. For our directional derivative, we need a unit vector in the given direction. The magnitude of v here is 3, so our unit vector in that direction will be 1/3 times the vector 2, -1, -2. Now our directional derivative at the point will be the gradient at the point dotted with that unit direction. So we plug in pi over 6, -2, 0 into the into the gradient. We should get a -1/2 times I, a 0 times j, and a -√3 times k. When we do our dot product then, here we'll get a -1/3, and then a plus 2√3/3. So if I combine and factor out a negative sign, I get -1 minus 2√3/3 as a directional derivative. All right, so clearly, it's pretty clear, I think, that you can certainly go many directions from one point on a surface. If you start on a surface, there's lots of different ways you could go. If you imagine standing on a hill, for example, you could go up the hill, you could go down the hill, you could go alongside the hill, you could go diagonally up the hill or diagonally down. There's lots of ways you could go. However, there's only one direction that maximizes the directional derivative, and that direction is going to be given by the gradient vector. The way we see this now is to take advantage of this dot product that we just came up with on the previous slide. The directional derivative is the gradient dotted with the unit vector. We know that we can rewrite the dot product as the product of the magnitudes times the cosine of the angle between them. Since we're talking about a unit vector, the magnitude of u here is 1, so we just get the magnitude of the gradient times the cosine of the angle between the two vectors. Certainly this expression is as large as possible when cosine is as large as possible. So that means that our cosine would need to be 1 or when theta is equal to 0. If the angle between the two vectors is 0, that means our gradient vector and the unit vector are parallel to one another. Or more specifically, they're pointing in the same direction. So therefore, the gradient vector is giving us our direction of maximum increase. Also, when cosine of theta is equal to 1, the magnitude of the gradient is that maximum rate of increase. So for this example, we're asked to find the maximum rate of change, of the function f of xy equals y natural log of x at the point 3e², and the direction in which it occurs. Find our gradient vector. Derivative with respect to x is y over x. Derivative with respect to y is natural log of x. So our gradient vector is y over xi plus natural log of xj. The direction of our maximum rate of change is the gradient vector evaluated at this point. So we put in 3e² for x and for y. We get 3 over e²i plus 2j. That's the direction that indicates our maximum rate of change. The magnitude of this vector now is the maximum rate of change, and if you go through all that work, you should get square root of 9 plus 4e to the 4th all over e². Let's look at how gradients and level curves and surfaces behave with each other. So remember, to create level curves, we can set the function equal to a constant and then graphing that curve, f of xy equals k, in the xy plane. Further, let's suppose that we've got a vector valued function that represents the curve. So that means that I can plug in the x of t, y of t. I should plug that into the function. I should get k, because we just said that vector valued function represents the curve. Let's take the derivative with respect to t on both sides and use the chain rule to evaluate the left-hand side's derivative. So now we get the partial with respect to x times dx dt plus the partial with respect to y times dy dt. That gives us 0. I can split that as a vector dot product, or I should say rewrite that as a vector dot product. And then I recognize the first vector as the gradient vector and the second vector as the derivative of our curve. So this says the gradient vector is orthogonal to the derivative of the function. So remember, the derivative of the function gives us the tangent direction. So this tells us that gradient vectors are orthogonal to tangent vectors. Okay. So let's use an example. Do this with an example. Let's show that any line tangent to a circle is perpendicular to the radius. So let's say that we just simplify everything. Let's do a circle of radius r centered at the origin. So then we have the equation x squared plus y squared equals r squared. We can also parameterize that circle as r of t equals r cosine t, comma r sine t. Let's say we have a point AB on the circle, and our function is going to be x squared plus y squared. Then let's take the gradient of that function. We get 2x comma 2y for the gradient. The gradient evaluated at the point is 2a comma 2b. Notice that the gradient points in the direction of the radius from the center to the point AB, because it's just 2 times AB. So the gradient is pointing out from the center, 0, 0, out towards the point to the point AB. Actually, it's twice as long, right? It's 2 times the vector AB, so it goes through the point AB, if you will. AB is also on the circle, so certainly there exists a t value that we can plug in that gives us the vector a comma b. If we take the derivative at that point, notice that we get the vector negative b comma a. That's going to be a direction, that vector that's tangent to the circle. And now notice that if we take the gradient and dot with this tangent vector, we really do get 0. So we really do get the gradient, which is also representing the radius. It's in the same direction as the radius. Dotted with a tangent is equal to 0. So we really do get that radii and tangents are perpendicular to each other in a geometric sense. We can the same principle applies for level surfaces. If we have a level surface, and we have a continuous vector function on the surface, then the gradient and the derivative are 0 for any point that lies on both the surface and the curve. All right, so remember that our derivative is going to lie in the tangent plane to the surface, no matter what direction that we're talking about through that point. So we can conclude that the gradient vector is giving us a normal to the tangent plane to the surface, just like the gradient vector was normal, orthogonal to the tangent vector for a curve in the xy plane. So since we have a normal to the tangent plane, that means now we can write an equation of the tangent plane in terms of the gradient vector, or the partial derivatives. So we get the partial with respect to x times x minus x naught, plus the partial with respect to y times y minus y naught. Same thing with the partial with respect to z times z minus z naught equals 0. And we can use that now to find an equation of a tangent plane to a surface, to a level surface, I should say. It also works if we have just a tangent plane to a function of 2 variables, z equals g of x, y, because I can think of that as a function of 3 variables, and then I want the level surface equal to 0. So we can use the exact same equation. It's just now that your partial with respect to z turns into a -1. So this gives us the equation of the tangent plane for tangent to a surface, g of x, y, at the point x naught, y naught, and that agrees with our formula that we came up with before for tangent planes. Let's say now we're asked for this final example here to find equations of the tangent plane and the normal line to the surface xy plus yz plus zx equals 5 at the point 1, 2, 1. Find the gradient vector first. We get y plus z, x plus z, and x plus y as our 3 components of the gradient. At the point 1, 2, 1, we get the point the vector, 3, 2, 3. These will give us a normal vector to the plane that we're interested in for the tangent plane. Oh, and I have a typo here. This should be a 1. So this should be 3 times x minus 1 plus 2 times y minus 2 plus 3 times z minus a 1. That should be a 1, not a 3, equals 0. And remember also that if we want of the normal line that we're interested in, well, the gradient vector here again is giving us the direction vector for the normal line. So we can use our usual parametric form of the line to get us the equation of the normal line.